man, how does he get away from the 2? Oh, that's right. The 2 for the 2 appearing in the constant is for the cosine series, not for the full series. Yeah. So that is a very, very slick way of capturing what the Fourier series is. I mean, in the complex notation, the distinction between sines and cosines gets washed away, and we just replace them with an imaginary exponential and complex coefficients. And then he says some disparaging remarks about this because he doesn't have any intention of using it. But I think that understanding this is a worthwhile goal, and it probably helps you understand quantum mechanics better.
What would be, like, the disadvantage to that? Because, like, in my mind, I think, you know, unless you don't enjoy moving into the complex plane, but that seems
That's the main
easier.
thing, is people are uncomfortable with imaginary exponentials. And you may or may not, I'm not sure I entirely understand everything I just did. I really have to sit and think about this business in here.
Right.
No, it makes sense. I mean, so if m is negative, it's fine, m is negative, right? But this becomes a sub m plus I b sub m. So it's always a sub m plus I b sub m for all m. Which is why we can collapse both of these into one sum from minus infinity to infinity.
Is it supposed to be like negative m, or is it just m?
Which one?
Like for the coefficients there.
That's a minus. There's a minus here and there's a minus here.
No, I mean for like the sub, like the m. Is that just notation or?
Well, that's because we made a change of summation from n to minus m. M equals minus n. But then again, the a sub minus m is equal to a sub m.
Yeah, okay.
And the b sub minus m is equal to minus b sub m. So, with that,
Okay,
these are the same. Just one goes from minus 1 to infinity, the other one goes from 1 to infinity, and then the other one's just out here. But if you think about imaginary exponential of 0, that's just 1.
Yeah.
So that gets in that monkey in the middle.
That's very clever.
Anyway, we'll probably do more with this at some other point, but I was hoping to show you guys an example from quantum mechanics if we have time. Do you have time?
So we have like 10 minutes.
10 minutes?
45.
Yeah, I think. Maybe. I don't know. 10 minutes a little bit tight, but I'm gonna go for it. So.
I can go a couple minutes over. I drove. I'm sitting in front of the mall. So.
Yeah. So this is Introduction to Quantum Mechanics by David Griffiths. As you can see, we have a dead cat, or I've been told the cat is sleeping. I prefer to think that the cat in the back is dead.
I don't.
Would make more sense.
So psi is the wave function, and as you remember, I was having some crisis of notation before. So here's what we're going to say. I'm following Griffiths, which is what I was trying to find last time. It was driving me nuts. So this is the wave function, the honest-to-goodness wave function. This is what he calls a stationary state. So you have the full-blown Schrodinger equation, which is, what was it? It was, oh come on, it's killing me. Schrodinger's equation is what? It's I, h bar, the, grief, partial psi, partial t, equals to what? Minus h bar squared over 2m, partial squared psi, partial x squared, plus the potential energy times psi. So you do separation of variables, right? You plug in this separable solution, and you get yourself like I h bar df dt times the stationary state is equal to minus h bar squared over 2m stationary state prime prime of x. And you write that in terms of a derivative. D squared psi, little psi, dx squared, not capital psi, times little f plus v f psi, like that. And then, like we did the other day, we talked about this. We did the usual thing, right? We divided both sides by the full wave function, and that gave us I h bar f prime over f is equal to minus h bar squared over 2m psi prime prime plus v psi, right? And so we said that that's equal to a constant called energy, right? Energy is, so this is a function of x. This is a function of t. All right. So that brings us to the so-called, time-independent Schrodinger equation, right? And I'm sorry I spent so much time on this stupid theorem. I'd rather spend 20 minutes on what we're doing right now. I'm an idiot. It's bad timing today. Curses. Alright, so anyway. We get ourselves to minus h bar squared over 2m d squared psi d squared plus the potential energy times psi is equal to E psi. This is the Schrodinger, time-independent Schrodinger's equation. We have to solve this in order to find stationary states, okay? All right, so it's kind of an intimidating differential equation to try to solve, a little bit. But we can do it. All right, so since our time is limited, I will do the easiest possible example. The easiest possible example, I think, is the infinite square well. So here it is. V of x is 0 if 0 is less than or equal to x is less than or equal to a, and it's infinity otherwise. So if I was to draw a potential energy diagram, it's kind of like this. But that doesn't quite do it justice because it's infinity. Okay. All right, so we have to solve this differential equation, right? We've got minus h bar squared over 2m d squared psi dx squared equals to E psi. This is for 0 less than or equal to x less than or equal to a. Right? He says, we have assumed, he says he's going to assume the energy is non-negative because we know from problem 2.2 that energy less than 0 doesn't work. Well, we're just going to have to take that on faith at the moment. He says, well, what are the appropriate boundary conditions for psi of x, right? He says, ordinarily, both psi and d psi of x, d psi dx are continuous, but when the potential goes to infinity, only the first of these applies. All right? Then he claims, I'll prove these boundary conditions and account for the exception v equals infinity later on. For now, we'll have to trust him. All right. Well, we're gonna assume boundary conditions. Psi of 0 equals to psi of A. All right. Equal to 0. Okay, so we got ourselves what? We've got let me rewrite it this way. We've got psi prime prime plus h bar squared. Okay, I need to multiply this by, I'll do a step here. Psi prime prime is equal to 2me over h bar squared, right? Or in other words, psi prime prime plus 2me over h bar squared psi is equal to 0. Right? So we can solve that. Am I in frame?
Yeah.
Okay. Oh, it's that time here. So this is what? Basically you were looking at psi prime prime plus, let's say, k squared psi equal to 0. Where your k is the square root of 2 times mass times the energy divided by h bar. And you guys know how to solve this. This is psi of x is equal to something like a cosine kx, right? Plus b sine of kx. Now, but psi of 0 is a, right? And that's equal to 0 by the boundary conditions that we don't entirely understand yet, but we'll talk more about some other day. All right? And psi of L, right? L? No, psi of A. Sorry, I've got L in the mind for some reason. Psi of A, right, is equal to B times the sine of Ka, right? So that has to equal to 0 as well. How can that be 0? So we must have that Ka is equal to what? Ka has to be equal to n pi. For some n equal to 0 or 1 or 2 or so forth.
Right.
So let's see here. In other words, let me go back up. I'll work over here, I guess. So I have square root 2me over h bar. That's my k is equal to n pi over a, right? If I divide this by a. So square both sides, we get what? We get 2me is equal to n squared pi squared h bar squared over a squared. And there you go. The energy of the nth wave function is stationary state, to be more specific, n squared pi squared h bar squared divided by 2 times m. So there you go. That's the energy of the nth stationary state. So the energy can't just be anything for the wave function. It's quantized. It goes in these discrete steps. You know, like this. And did I lose an A?
A squared, I think.
A squared,
the
yeah.
bottom.
And the smaller A is, the bigger the steps are, right? If A gets really big, the steps are pretty close together, aren't they?
Mm.
Of course, h bar squared is stupidly small too. So, but in the case A is very, very small, then these are, you know, there's some kind of. So, just to draw some wave functions in, since I've already gone this far in, And I hope I can show you guys more examples like this. My intention is to work, spend a couple hours in here just fiddling around with quantum mechanics examples. I think it's healthy for you guys to see some, since you're thinking about, I don't know where I put the cap of this thing. I dropped it. I don't know where it went. Well, this one's better than that one, I guess. It's like the design who goes on a lifeboat. See here. Yeah. Color. So n equals 1, something like this, right? That's n equals 1. It's just a sign. There's one node. N equals 3 is something like, I'm not sure if I'm doing it right. It's sine of 3x, right? Oh, I'm sorry. How about n equals 2? I'm an idiot. If you have sine of 2x, right, you go, and then you just keep, I can't do it worth anything, but, the more of these, the higher the energy. Those are the only possible energies for this infinite square well. Okay, so later, some other day when we have more time, it'll take me much longer to do the other problem. And hopefully when we come back to this, we'll try to explain some of what the logic is here, all right? But in this is actually not, my picture is not an infinite square well, right? This is actually a finite square well. And what you learn when you study the finite square well, what we'll learn is that we have things like this, and then there's actually there's this tunneling out here. There's like some probability the wave function will go into places which are classically forbidden. Like out here, classically would be like negative kinetic energy, but quantum mechanically, there's this tunneling phenomenon which is allowed, which ultimately means if you have something like this kind of bound, if you have a potential that's like this, you could even have the situation where you get tunneling and then it comes out the other side. This is why people say in quantum mechanically there's some probability that you could just walk through a wall, because you could tunnel through it and come out the other side. It's fantastically small probability, but it exists. So I hope we can derive that some other day. But anyway, I shut up.
No, I have.
It's like